Here's another example of how you use F equals ma, Newton's second law, to solve various problems. We're going to do the Atwood machine problem again. That's just another word for a pulley. And this time we're going to use a technique called free body diagrams. So how does that work? Well, let's read the problem first. We see here we have a string that is placed over a massless and frictionless pulley. A mass of 8 kilograms is suspended at one end, while a mass of 5 kilograms is suspended from the other end. What is the acceleration of the system? So the first thing you want to do is, again, draw a diagram of what's going on. So here's a ceiling. From the ceiling, we suspend a pulley. From the pulley, we will suspend two masses, a big mass, call it M1, and a smaller mass, call it M2, realizing the big mass has a mass of 8 kilograms, and the small mass has a mass of 5 kilograms. All right, and of course we realize we have tension in the string, so we'll call the tension on the left side tension 1, we'll call the tension on the right side tension 2. And we now have to try to find the acceleration of the whole system. The way we did it before was to consider the whole system as one unit and only look at the forces acting on the system, so we ignored the forces internal to the system. We didn't talk about T1 and T2. But now what we're going to do is we're going to draw a box, so to speak, around each of the masses, and then look at all the forces acting on each of the masses independently. So we draw a box around that one as well, like so. And let's draw those boxes over here. So box number 1, we have M1. Over here, we have, so let's draw a box like this, suspended from a string. Over here, we'll draw the next box. We have mass 2, and also suspended from a string. So let's take a different color now and mark on each of those boxes all the forces acting on each mass separately. So in this case, we know that we have the force of gravity acting on the first mass, so that's M1G. And then we have the tension pulling back up, which is tension 1. Now, of course, we realize here that this whole system will accelerate. Since M1 is bigger than M2, we can assume that the acceleration will be this way. We'll call that A going in this direction. Of course, this mass will accelerate upward. So we'll call that also A. We call this A1 and A2. And since the two masses are attached to a string, you can, of course, see that the acceleration, the magnitude will be the same. They'll just be in opposite directions. On this one here, we have the force of gravity pulling down, which is M2G. And then we have the tension pulling up. Let's call that T2. And then, of course, using the equation F equals ma, we can now write the equivalent equation for each of these two free body diagrams, as we call them. We took each body by themselves and drew all the forces on it. All right, we have T1 acting in a positive direction, so that's a positive force, T1 minus M1G pulling down a negative direction, M1G, and that equals the mass of the body, which is M1, times its acceleration, A. And let's call this A1. All right. We'll do the same for the second block. F equals ma, we have tension 2 pulling up, that's a positive direction, minus M2G pulling down, M2G. And that equals the mass of the object, which is M2, times its acceleration, let's call that A2. So they will each experience an acceleration. M1 will experience an acceleration A1, M2 will experience an acceleration A2. So now we have to solve for the accelerations and then also ultimately for the tensions. So we have 4 unknowns. We have tension 1, A1, tension 2, and A2. That's 4 unknowns, and we only have 2 equations. So obviously with 2 equations and 4 unknowns, you could normally not solve that. But then we realize over here that since there's one string here and the pulley has no mass and no friction, T1 must equal T2. That's a necessary condition for this particular problem. Also, looking at the accelerations, we know that the magnitudes of the accelerations have to be the same, but the signs are different. This one has a negative acceleration. This side has a positive acceleration because it's accelerating upward. This one is accelerating downward. So we can say that the one acceleration is the negative of the other. So we can say that A2 or A1 is equal to negative A2. A2 is positive. A1 will then be a negative quantity, the negative of the positive A2. That allows us to now substitute in for these variables. So since T1 equals T2, we can then say, well, then they must equal T, right? If they're equal to each other, we can just call them T. So we call this T minus M1G is equal to M1A1. Or I can say, well, since A1 is the negative of A2, I can replace A1 by negative A2. And at the same time, I suppose what we could do is we could replace the T1 by T2. So we call this T2 and call the A1 the negative A2. Like so. That's even better. On the right side, we already have a T2 and we have an A2, so we can write that T2 minus M2G is equal to M2A. Now we have two equations and only two unknowns, T2 and A2, and we can solve those simultaneously. So let's solve each equation for T2. We can do that by moving this across and applying the sign here. So we have T2 is equal to a positive M1G when we cross the equal sign minus M1A2. And on the right side, we can say that T2 is equal to a positive M2G plus M2A. Now you can see that we can set those two equations equal to each other. In other words, we could say that M1G minus M1A, 2, must therefore equal to M2G plus M2A, and this is still A2, so I better mark it as A2. There we go. And now we have one equation with just one unknown, which is A2. So we can solve for A2 by moving all the variables that have an A2 to one side and everything else to the other side. So we have a minus M1A2 minus M2A2 by moving this term over this side equals M2G minus M1G. Factoring out an A2 on the left side and a G on the right side, we have A2 times minus M1 minus M2 is equal to G times M2 minus M1. And then dividing both sides by minus M1 minus M2, we have A2 equals G times M2 minus M1 divided by a minus M1 minus M2. And then we go ahead and plug in the numbers, what they're equivalent to. So this is equal to 9.8 meters per second squared times M2, and M2 was 5 kilograms, minus M1, M1 was 8 kilograms, minus M1, which is a minus 8 kilograms, minus M2, which is a minus 5 kilograms. All right, when we add all that together, that gives us a minus 3 at the numerator, minus 13 in the denominator, so 3 divided by 13 times 9.8, which is a 2.26 meters per second squared. So A2 is equal to 2.26 meters per second squared to three significant figures. Notice that A2 was assumed to be a positive direction, and that's the answer we got. We got a positive 2.26 meters per second squared. Since A1 is equal to the negative of A2, so we can say then A1 is equal to the negative of A2, so therefore it's a minus 2.26 meters per second squared. And so you can see that indeed that is correct over here. We know that the magnitude must be the same because both weights are attached to the same string, so they must accelerate at the same magnitude of acceleration. But A1 is a negative direction, so we get a minus 2.26 meters per second squared. If we now want to find out what the tensions are in each case, since we now know what A1 is equal to and we know what A2 is equal to, we can then solve that for T1 and T2. So T1 is equal to, when we move the M1G over the other side, we get a positive M1G plus M1A. And so M1 in this case would be 8 kilograms times G, which is 9.8 meters per second squared, plus M1, which is, let's see, still 8 kilograms, but now we have to multiply the times A1, and A1 is a minus 2.26 meters per second squared. And when we multiply that out, I remember the answer, it is 60.3 newtons on tension 1. And then you can do exactly the same for tension 2, and you will get the same answer. So let's try that. So tension 2 is equal to, and we move the M2G to the other side, we get a positive M2G plus M2A. When we plug in the numbers, M2 is 5 kilograms times 9.8 meters per second squared, plus 5 kilograms times 2.26 meters per second squared. And if you multiply that with a calculator, you will also get 60.3 newtons, again showing that the tensions are the same on both sides of the equation. Now this is a much more difficult method, much more comprehensive method than the method I showed before, but at least in this case you can see that if you're strictly adherent to the directions of the accelerations and you look at each mass separately in free body diagrams, eventually you will get the exact same answer. All right, hopefully this helps you solve these types of problems.